Hello there people and welcome to the final Eduqas live stream. Yes, it is Saturday the 15th of June. It is 6 p.m, well 6:01 anyway, and we're going to do component 2 computer science. That's right. We're finally putting Eduqas in the bin. This is it. This is the last thing. Give us a hello in the chat if you're there. Let's see who we've got in tonight. Let's see who we have in tonight. Oh, great. This is where it starts. I have no idea who these people are. Names, not a clue. Hello, hello. Don't start calling out thumbnails. All right. A few people here with us. Hopefully, we're going to get you through your exam on Tuesday, the 18th of June. It is an afternoon exam. Okay, it's an afternoon exam, people. So, on screen, you'll see our typical live stream layout. We've got a number of different chapters in Component 2. We have 8 in total, starting off with hardware and communication and ending with data security and integrity processes, people. The highlighted yellow parts that you see in each of the chapters are what came up in 2023. Now, we'll talk a few people through our 2023 exam because 13% of that paper, 13% of that paper was on binary systems. So that's things like calculating binary numbers, mantis exponents, positive, negative, binary addition, subtraction, all that good stuff. 13%. Now, typically, 13% of binary systems, that's about right. That's about right. Databases, it tends to always be 10%, always. So if you can master databases and binary systems, then that's, in that exam last year, that was 23%. Look at my maths, that's incredible. I'm adding numbers together. 23%. That'll get you in the category of E and D range, which is all right. Assembly language has come up a few years. I added that in there because people get scared of assembly language, but it's 6% in that paper. It was last year. So let's go and have a look, shall we? So the paper, it was a tough paper last year, and I think Blob, I don't even know how you say your name, right? Paper 1 was actually really good this year, and I think that a lot of students were pretty happy with it. I think nobody complained to me, actually. Usually, students get out and go, John, you've ruined my life. What are you doing? It was actually quite good. So that's excellent work, people. I think you all, most people prepared themselves quite well and put in the time and effort needed to actually get a good results on that one. So if you look at it, last year's paper 2, was actually quite hard. It come up with some really, really obscure, random parts of the specification that caught a lot of people off guard. We talked about QR codes there, and 3 advantages of QR codes over traditional barcodes, which looks at that is input. So looking at input things there, input devices, and how to take inputs from people. Then it talked about this one, again, predictive analysis and analytics. That comes under databases, so data mining, predictive analytics, taking lots of data and then predicting things from that. We also had a large part of databases, but the first bit of it was a bit cheeky, looking at data redundancy, consistency and independence and how they all interact together. And then it started to talk about relationship diagrams. So ERMs are usually pretty good for students. And then it was a whole database structure in third normal form for a booking system. We're going to have a look at those a little bit later on. But yeah, that was your 10% of databases in there. Just realised, though, it was more than 10%. It was 13%. Assembly language question. We'll have a go at that later on if people want me to. I have got that one sort of prepared in the back later on for that. Also, moving a bit further down, it had a little bit of operating systems. Now, they like to jump in to operating systems. Operating systems is a really, really big part of the specification. It takes quite a while to teach it, and it's quite technical in certain bits. If I move down to the bottom, past all this, SQL appeared there again as well. SQL, so more databases. Oh my days. This was quite cheeky of them. Give you an algorithm there, and that algorithm was actually a Caesar cipher, so that comes up in cryptography, which is 2.8 data security. In answer to the question there, Joel, this is absolutely WJEC, but technically this is Eduqas because I am in England. That's right, I am in England right now. Networking came up at the bottom. Who asked me about that 12 marker down there? Who was that? Thoughts on partitioning of main memory question last year for no marks. I thought that was absolutely a disgusting question, that one. 12. Did not like that at all. Not a fan. And I'll talk a little bit later on about the end, what the last questions are all about. So if you're in my Google Classroom, hopefully you've seen my tracker of what questions come up year on year on year. And what did the people ask for? What did the people ask for?
And like a lot of us are really smart. I'm really smart.
Oh yeah. People asked for... There you go. The things in green, all of that is what my students have asked me for to cover in this live stream. That person who fails to see the difference between Dijkstra's and forwarding table, so can we go through the forwarding table question? Potentially. The forwarding table is just looking at it objectively. Dijkstra has a specific way to follow through the algorithm. A forwarding table you can do just by looking at it. They don't care about which way you look for the fastest route or how things are calculated. Whereas Dijkstra's is you must flood fill, so you must go node by node, working out the smallest associated cost and then working your way to the end and then finding out the fastest possible route. Yeah, that's right, Joel. There's a crossover. There is a crossover. Christina, the FDE cycle is fetch, decode, and execute cycle. Then purple ones have been through, come up last year, and also shifting came up last year as well in binary, but I didn't highlight that. Don't know why I didn't. But expert systems, I'll go through that first time, I think. And I think weather forecasting, so CAD, robotics, and CGI, again, large mark questions. Only stopping by. Good luck on your exams, Louis. Wow. People, you won't need it. You will not need it. Now, we did quite well, didn't we, at guessing component one? I can't promise I'm going to do that again. That was a sheer stroke of luck. Segmentation and paging. It's a little bit. Main memory, yeah, it is in there. So should we jump ahead and get stuck into some of these questions? Shout out to Majid, who asked, give me a few topics to go through specifically. Emailed me earlier in the day. I hope it's better. I hope it's better than last year, because last year was horrid. I really do. So let's jump to expert systems. Now, what I'll do is, I think 2.7 is a really quick part to go through. So I think I'll just glance through this nice and quickly for people. Now, if there are any things that people want me to go through more specifically, Louis, aren't you an IT technician? I'm pretty sure you're an IT technician now. Is that right? I don't know. You can let me know in the chat. So types of software. What are we specifically talking about with types of software? These are quite easy for students. If these come up, we are laughing because you've got open source, bespoke, and off the shelf. All right? I know where you work, Louis. I've got sources in that school. So open source, usually free. If you can program competently, then you can customize to your own needs. Open source is good for everybody. Everybody shares the love. All right. Now you've got bespoke software, which is specific for your needs, which means it can be incredibly expensive. So software isn't immediately available because you need to design and develop and implement it. The government goes down the route of bespoke software, and usually it's an absolute joke. It runs over budget all the time because it's really poorly managed. Off-the-shelf software, you can thank Bill Gates for implementing the world's best off-the-shelf software, which was Microsoft Office. Cheap, but not as cheap as open source. It is readily available and on demand. So it's usually quite generic as well. All right. Yeah, proprietary. Yeah, correct. Now, if we move into sort of software that is safety critical, if we talk about safety critical systems, then really we're focusing on things that have a human life risk usually, and they cannot be allowed to fail. So you might ask yourself, well, what kind of systems allow death or serious injury if they fail? And also, critical systems talk about loss or severe damage to company assets and also damage to the environment or wildlife. And you might be saying, John, why are you talking about the environment, wildlife? Well, because our water companies have been dumping lots of sewage, and they blame certain systems and softwares and all kinds of stuff as a part of that. Whether you believe that or not is your choice. It's up to you. So moving on, we've got a couple of examples that you could use in your exam, and notice how none of these are brand specific. Yes, don't use brands in your exams, people, because you're assuming the examiner has knowledge of that, and they do not. So firstly, the examples there. What about train door locking mechanisms, level crossings, and self-driving cars? All right. Industrial processes such as nuclear reactions. Yes, nuclear reactions. So think about Chernobyl there. That was a bad one, wasn't it? All right. Now, safety critical systems. In case a failure does occur, you have backups. So you have things that will prevent or limit the damage. So firstly, you've got a fail-safe system. So these are the ones where manual overrides are in place should a failure occur. So let me point you to a cockpit in an aircraft. If the pilot falls asleep and something starts to happen, an autopilot disengages, you have a yoke in the middle which basically violently strikes the pilot's knees to get their attention. All right, that's a fail-safe system. You also have fault-tolerant systems as well. And there'll be redundant systems in place, and they are split out into sections. Should one section fail, then it can be bypassed, or a redundant system be brought online. Now, nuclear reactors usually have these fault-tolerant systems because if something does fail, there is a backup in place ready to pick up. And that might be like cooling down the cores and things like that. Fail-passive systems are ones which will operate in the event of failure. When autopilot fails, the pilot must be able to gain manual control. So the pilot's on hand. Technically, fail-passive system, making a fail-safe system, the pilot is there to back up and get his hands on the aircraft. So, if we talk about other types of software, we have weather forecasting, computer-aided design and computer-aided manufacturing, and robotics and CGI. It's been an awful long time since they've asked questions about these for large mark questions. So, I'm kind of 50-50 whether these will come up or not. 50-50 whether they'll come up. But weather forecasting, if you look at the mark scheme for the last question that came up on weather forecasting, you can break it down into inputs, processes, and outputs. You have lots of sensors with weather forecasting, like temperature, pressure sensors, wind and speed direction, moisture sensors, processes. Now, weather forecasting is one of the most complicated systems, and we actually need supercomputers to work this out. We've got years and years of historical data that we can all add together, and you can bring all these hugely complicated calculations all together to predict with geographical models and find out what on earth the next day, 5 days, is still what they're doing. So the problem with that is you spend a lot of money on it and still they get it wrong. I don't know how. Also, you have outputs. So you can produce localized predictions of temperature, wind, precipitation, with the accuracy diminishing the further forwards predictions are made. So we have 7-day forecast, but wasn't great. Yeah. Slides in the mega. No, this is part 2, so there'll be a new mega PowerPoint. This is another mega PowerPoint. This is just for component 2. This I split them into 2. Otherwise, it would have been so vastly large, it would have blown your mind. All right. At the bottom there are some bullet points that are out of the mark scheme, because think about it, with a 9-mark question you could give the pros and cons, can't you? Pros and cons. Data transmitted all around the world, inputs into a supercomputer, calculations are performed based on current conditions, and predictions are based on previous understanding and the current grasp of scientific understanding. Parallel processing is often used to share the load and not always 100% accurate because it's the weather. So what do we look at? Look at these. Oh yes, that is the supercomputer. It's powered by Microsoft at the Met Office. And if you think about the amount of data that's actually finding its way to that server, it is astronomical. There are weather stations, so you can see the different types of weather stations on the bottom screen there, taking in all kinds of inputs and all finding its way back to the supercomputer. Does anybody know how it gets back to the supercomputer? What technology it uses to get back? Are they wires? Is it wireless? Any idea? How does that floating boy in the sea actually find its way back to the supercomputer? Anyone in the chat have a know? Anyone know? Satellite, that's a good one. Yeah. There's something. Yeah. The ones on land actually don't use satellite because it's way too expensive. They use 4G. Some of them use 3G as well because it's even cheaper. But typical smart meters now, if your parents have a gas and electric meter, they might be on a smart meter. That uses 4G as well. So we don't have to record and send back stuff anymore. So, same thing. In P1, parallel changeover. Yeah, well, parallel changeover can be used for safety critical systems. That's fine. Yes. Solar to transfer data. No, fiber optic. Yeah, you wish. No, not really. It's too expensive, fiber, for doing that. We need wireless systems. So if we look at computer automation and robotics, computer automation refers to when some form of computer system will control something in the physical environment. Now, the computer gathers inputs using sensors and it produces outputs using actuators. Actuators are just electricity goes in and motors do things. That's it. So when you think about computer automation, you have a feedback loop. The feedback loop are where sensors take readings, change is detected, we then process the new data, and then we make a change to the physical environment, and it goes to reading in sensors again. The great thing about robotics is that they can take in way more inputs than you and me. Our brains cannot operate that fast. Computers are way better, and that's why the argument is, well, what about automatic self-driving cars? Are they safe? You're damn right they're safe. They're safer than you and me. They can take in way more inputs than you and I can. They can tell how fast we're going, what the road conditions are, whether there's people on the left or right. They can detect everybody else on the road. You can't do that. So when a sensor is used to record data, it'll be processed by a computer. You need to make sure that the change is detected, the new data is processed, you make the change, and you take more readings. Now, if you think about how we design these systems, what's good is when we used to design them, we used to have prototypes. So big companies like General Motors, Ford, etc., they'd build an actual car out of clay or foam, and they would put it in a massive wind tunnel and they'd test it, and it would be like, okay, well, it's not very aerodynamic there, it's not very aerodynamic there. Nowadays, we create it super fast, super quick on computer-aided design software. We will edit the shape and we'll put it through physics engines in software to tell us how aerodynamic it is or how structurally sound the materials are. That's how advanced these physics are nowadays. And we'll just keep feeding it. The better our understanding of these systems are, the better technology we have, and it also makes it cheaper for you and me. So benefits, we've got quick prototype changes, we've got stress-free stress testing with physics, like I just explained, and also 3D views. Now, architects are using virtual reality and mixed reality now, so that people can see what the building would look like in the future. And you can have building walkthroughs for customers. And there's no material cost for that. You know, there's no 3D printing involved, no actual building of anything, and that's all wonderful. So if you look at those images there, that was the world's first 3D printed car. Nice and lightweight. Electric vehicle. Is that where we're going, people? Is that our future? Now, when it comes to designing it with computer-aided design, the computer-aided manufacturing side of it, the systems will actually produce it. So you put your design into a 3D printer and it prints it. It could be nowadays with computer-aided design, and manufacturing, we have robots that can actually produce and carve metal. They cut out metal very specifically, and they can build really, really complex shapes that we can't do. Okay? So are all these contemporary applications? Yes, they are. They're contemporary applications of software. And the good thing about computer-aided manufacturing is that they will always produce products that are exactly the same. They don't get tired. They just keep running all the time. And they don't make mistakes unless they break down. And that's where we come in. We have to come and fix them. They can work 24/7. And with that, with the fact that they can work 24/7, they outbeat us. They don't require smoke breaks. They don't require a pension. They don't require holiday pay. They don't require maternity or paternity leave. So people in business are moving towards automated computer-aided manufacturing. And one recent example that I saw reading in the news is that houses are being made now just by robots alone, by printed concrete. They can do it in a day because they can work for 24 hours, and they can build really complex designs and make sure that they are structurally sound. Can you say they're also as good as the programmer who created them? You can, yes, you can. With these systems, they are rigorously designed and tested. And now with AI machine learning, I think that even when they make mistakes, now they might start figuring out what they have done wrong. That's a scary thought. And is the problem of more morality of putting robots 24-hour work and the responsibility when stuff goes wrong? I suppose you could say that. You could say that. You've got to balance the argument here. So again, I've put it in inputs, outputs and processes for you. And you can have a look at that. This is in the slides, but you're probably aware of these. You know, computer-aided design and manufacturing, mouse, touch screen, even a pen that I'm holding with my graphics tablet. You've got processes, so calculating the cost of making the components, how structurally sound it is. Outputs, it could be still images on the screen, it could be animations or walkthroughs, or even tabulated costs of what you're trying to create. And it's all good. You've got access to all these sensors. Your phone has most of these sensors. Your phone even has a humidity sensor. I don't know if you've ever come across this, where you might have got some water in your charging port and you try and plug your charger in and your phone says, nope, not today. No thanks, can't charge it. You've got water in it. You're going to have to let it dry out. Infrared sensors, when you put your phone to for your face, you've got proximity sensors there. Accelerometers are detecting whether you're walking or not. And you've got pressure sensors as well. So, B Grant Music, you would say it's best to do the 2020 past paper or last year's for component 1. At least they seem to repeat everything every 4 years, and doing the 2020 paper really helped for this year. I would say that a blend of most papers. My students have access to a sort of a question tracker throughout the years, so they can kind of see what's reappearing. But definitely binary and definitely SQL. Comes up every year. How many exams do Eduqas have? Well, this specification started in 2016, so it's quite a lot. If you take out the COVID papers, you can do the math on that. So yes. Now, what problem do we have with automation? Oh dear. Yes. People are taking your jobs. Sorry about that. I say people. Robots. Computers are taking your jobs. Yeah. Gone are the days of Debbie in Morrison's scanning all your produce. Now she's been sacked and been replaced by a machine. Yeah. Yeah, Tesco got rid of her. And the machines keep expanding. They do have problems, they do have flaws, but they're getting ironed out. The touchscreens in McDonald's, terrible, they're dead slow and they annoy me. It's like they've invested in the cheapest, huge tablets they could get their hands on, McDonald's, stupid people. Yeah. 4 or 5, I forgot. So yeah. But McDonald's, good on you.
And a lot of us are really smart. I'm really smart.
Yeah, they're really smart. Now then, robotics. If that pops up, what we're going to talk about? Oh my goodness, what we're going to talk about. We've got here Inputs, combination of program code and the input from the sensors. That's all they have to go off. They can process it really quickly. All the information is highly reliable. They do not make mistakes. The only mistake that they make is the inputs and the outputs. If it's been programmed correctly, they will never make a mistake technically. Okay, Walmart in America is trying to make people subscribe to use self-checkout. Yes, because they want to get rid of people. Think about club cards. What they're taking your buying data, aren't they? But that's more about data analytics. That's later on that. Robotics can be programmed to do anything. Primarily production and exploration. Warehouse systems. We're thinking basic jobs here. So if you don't want your job to be taken, you have to think about it. You have to think about what job you're going to have in the future, and that a computer can't take it. Then we move to something that's actually got quite a lot of traction. I've had quite a few students go to VFX. Anyone ever heard of VFX before? Anyone know what it stands for? So if you think about computer-generated graphics and CGI, drawing packages allows for 2D images to be developed into 3D. More 3D, advanced 3D software modeling is now very popular. It's visual effects, yeah. So a lot of computer science students go for visual effects at university because it's incredible. What you can do in visual effects now is scary. And you see it develop, don't you? You see it now morph into things like, film. Think about Lord of the Rings and, Guardians of the Galaxy and stuff like that. We have techniques called ray tracing, where you trace the path of light as pixels in an image plane. And what that does is it allows for light and shadow and the movement of light. Okay? And VFX people are used in almost every film now. Every single film almost are using VFX. Oh, it's a great degree to have in the future. Absolutely. Unreal Engine. That's a really good gaming engine to use. There is another one as well. It slipped my mind. Unity. Unity also does that as well. These are like professional. They're free to download. You can get started in them straight away. And there's loads of things on YouTube that you can actually use for this. But CGI and animation, inputs. So we've got photographs, bitmaps, vector graphics. So vector graphics are when you sort of expand an image. Do you need all this for the exam? Well, if it's a 9 marker, yes you do. Because the 9 marker will be on one of these, I imagine. And Mohid, if he's here, he asked me to talk about control systems. Control systems. Control system is a system that interacts with other electronic and or mechanical systems. A control system might monitor the temperature in your home and turn the heating on. Perfect example. You might have heard of Hive, for example. So as I leave work, and during the winter months, as I leave work, my location data on my phone tells the app of Hive that I am on my way home, and it will start the heating process for me, which means it's nice and warm when I get home. Fantastic. Great work, control systems. So we see control systems in a lot of IoT devices, Internet of Things. You've probably got devices in your home. Can anyone tell me what IoT devices they have in their home? I'll rule out Alexa, Google systems, because everyone's got one of those pretty much nowadays. I don't. I'm not bugging my home. Search engines are part of... Yes, search engines are. Nest. Yeah, Nest. That's a good one. Even things like, what are them, vacuum robots? Your TV. Yeah, your TV is a part of it. Yep, smart TVs. Alarms. Great work, yes. Alarms nowadays. Again, they detect when you leave the house and they'll basically alarm themselves or arm themselves. Wonderful. You can have lots of lights as well. Roombas. Yes, the Hoovers. I'm looking at purchasing one of those for my college because it's a great bit of kit. Some washing machines, yeah, even kettles. Brilliant. Okay, so now we move on to knowledge-based systems. Now, I've got a feeling, don't quote me on this, people, but I've got a feeling expert systems might be coming up. Don't know why. It's a gut feeling. What is an expert system? Sometimes they're referred to as knowledge-based systems or KBSs. So don't get caught out in the exam if they use the word knowledge-based system because it just means expert system. An expert system is a system where the user, you and me, can interrogate a vast knowledge base to find a solution. The knowledge base is usually a database, and the user enters information that they might have. And the knowledge base will then infer an answer based on a confidence level. A kettle might need Wi-Fi because I'm sat in the front room. I don't want to walk to the kitchen to turn it on. I want it boiled at a certain temperature. Tea has to be a perfect temperature, people. 85 degrees, my tea. No more. Don't need 100. It's wrong. Yeah, Yorkshire tea only. Have I got any Yorkshire tea fans out there? It's gone quiet. Yorkshire tea fans. Come on, don't leave me hanging. Yeah, Yorkshire tea fans. No. Okay, no. All right, moving on. PG tips. You kidding me?
And we say bye-bye.
No thanks.
And we say bye-bye.
Coffee?
And we say bye-bye.
That's right. Okay. We move on. Dearie me. Now then, knowledge expert systems. 4 different layers to it. If this is a 9 marker, you've got knowledge-based systems, inference engines, the rule base, and the user interface. So in stage 1, the knowledge-based system, that is where you and me, experts in our field, could be doctors, for example. I like to go down the medical route on this because it's really useful. The NHS are trying to build something like this now for the 101 system, where you basically rock up and you click which bits you want, but it needs to be built by medical professionals, and they put all of their knowledge and information into a database, and all it is basically if-then statements, because if I've got a runny nose and I feel tired and I've got a cough, then it might be COVID. Yeah, stuff like that. Then what happens then after the information's loaded into a database, we've got our knowledge base, the inference engine applies the rules to the known facts to deduce new facts. So an inference engine attempts to work out the answer to the user's query by using the rule base. Is there an exam board example of an expert system? Teachers have always used Akinator, which is an example. Yeah, I remember Akinator, but we can't use that in the exam for obvious reasons. Well, no, you can't. You're right. They use something, OCR use something called Exam Builder. It's not quite an expert system, but it has like a big knowledge base of all the exam questions split up by topic. Don't use Akinator, no. Just talk generally, like medical systems. Think about car diagnosis. You know, when you go into a garage and things like that, it'll determine what's wrong with the engine based on a fault code, stuff like that. Now, after the inference engine, we move to the main bit, which is the rule base. Okay, the rule base. So the rule base is what links knowledge together through the facts. So the system works out the degree of certainty by applying the rule base to the user's inputs. If the degree of uncertainty that's determined by the system is high, then the system will spit out the answer. If not, more questions are asked to try and find a higher degree of certainty. If the degree of certainty is low, then the results are inconclusive, and what the expert system will do is ask you more questions. They'll go back and say, you've got a runny nose. Oh, have you had a head cold? Have you had any headaches? Have you felt tightness or pressure in the back of your neck? And it might try and work its way to an answer. If you say no, it'll go down a different path. Okay? If you say yes, it might increase the degree of certainty. So there's three outputs really. If it has enough information, it will output the answer. It needs more information, it requires more information from you, or it cannot reliably come up with an answer. So if it goes through and it says, oh, in actual fact, thanks for answering all these questions, but it's inconclusive, I don't know, it will not give you an answer. Now, it's important to point out that you shouldn't really rely on these for medical, if it'll tell you at the end, it'll give you a report, tell you the level of confidence, and the best ones tell you why it believes it's that level of confidence, and it might tell you to go to the doctors, book a GP, or go to A&E or whatever. The fourth part, which everyone forgets about, is the fact that you need a way of interfacing with the expert system. All right? So you need a way of talking to the expert system, and you do that through a graphic user interface, or a human computer interface, HCI. Right, well, we've got in the chat, Arthur, I need an example of one since I don't have one. Yeah, okay, that's fine. About 9 markers, like talking about the interface, defining what the interface is, like explaining data input, explaining the inference engine uses and rule base or whatever. Yeah, pretty much taking us through all of those 4 stages in a 9 marker will be plenty. That'll be enough. Just talk about. I'll give you some advantages in a minute and disadvantages of it, but there's benefits to using expert systems, and that's my medical one. The user queries it, and the expert feeds the knowledge base, and you get advice back out of it. People's time are not taken up. So that's for your 9 marker. Think about the benefits of using an expert system. You've got knowledge, can be accessed quite easily. You can, multiple experts can feed it. So the great thing is you can have the world's best experts building it. 24/7, it's constantly online. It needs to be kept up to date. Electronic systems are great. They don't get sick. They don't, as long as they're hosted well, they don't come down. It can reduce labour costs, or like real sort of basic stuff that doctors don't want to get tied up with. They can basically rely on expert systems to do that, or to triage people. And good expert systems explain the outcome of a decision, which I told you before. Okay. Now, I think in a 9 marker, you want to give a blend of opinions and really sort of show off what you know and what you don't know. So when I say that, I mean give the pros, give the cons, and then give your opinion. And when you give your opinion, base it on fact. So give the facts of it. All right. Mohid, I don't know if Mohid's here again. He asked for internet and intranet. So this is the back end of the software stuff now. Internet and intranet. What's the difference? Well, the internet is outward facing. It's the world. It's where everybody is. Most of the internet has been catalogued. I say most. It's not really. It's not really most. You've got the deep web, the dark web, and the World Wide Web. So the deep web is where military government organisations are based, private to them, encrypted, etc. The dark web is where people, where it's part of the internet that hasn't been catalogued or searched by big search engines. It's not illegal to go on it. You can have a look around it. If you look for crawling, ranking, and indexing, that came up. It came up in 20. Am I wrong here? 2022, I think it did. I don't believe it will come up, but you might want to look at it. Crawling, ranking, indexing. If you think about it, crawling is when you go across web pages and basically attract information and basically store it in a database. Ranking is how frequently things are accessed. It's how Google works, its ranking system. So based on that, the more searches, the more popular. If it's been crawled and added to database more often, then it will go up the ranking and people are searching for it. Indexing is basically keeping a catalogue of where everything is. All right, that is a very, very brief snapshot. And for things like that, I think AI is really good. So if you put that question, crawling, ranking, indexing into AI, it'll give you a couple of paragraphs on each one, and that's it. That's all you need. AI is brilliant for that kind of stuff. The intranet, when you look at sort of internet and intranet, intranet is like government, it's organizational based. Okay? So, internal. It's great because, one, you can host everything internally and you're not scared of people accessing your system. People can access from outside, but they need usernames and passwords to get in. All right? So with the internet, think physical. The internet. To define this for you properly, the internet is the physical side of it, which is all of your hardware. So it's routers, cables, satellites, servers, things like that, all put together to make the internet. We are all a part of it. My router is a part of it. Your router is a part of it. Over 5 billion people across the globe are connected on the internet, which is great. And the intranet first got brought in, I think it was the 90s. And what people did was they shared things between each other. You can connect to things, people. You can learn, communicate. You've got chat-based functions in there, so you can talk between organizations. Just like the internet on a smaller, much smaller level. And an intranet is like mini internets for organizations. Like I said, you can access out offline, so external when you're at home, but you're going to need usernames and passwords to do it. I think you're doing my slides, Namir. Yeah, it's definitely in the specification anyway. All right. So with an intranet, it has a reduced set of functions, and also it is a restricted version of the internet. The organization that runs the intranet has total control, whereas the internet, nobody has total control. That's the point of it. The intranet means that you can block certain things that you can search for, you can block things that people are doing. I will do, yes, I'll put them on Classroom, as I always do, being the consummate professional. All right. So its network comprises of all of its employees at senior level, and in some cases, partners, investors, and shareholders. Intranets typically use local-only networks. I'd say I'd add a little bit to it and say that people can control what happens on their smaller internet or their own smaller network. All right. Okay, wonderful. Now, talks about the difference. There you go. That's it, people. There are advantages. There are advantages to using the intranet. So think about this when it comes to advantages. Increases productivity between staff, cuts down on admin, creates operational cost saving, and it reduces errors. So that's things like lost data, lost files, etc. And also it improves access to information, and also it does encourage collaboration between people as well. And also in crisis time, so I'm thinking disaster recovery time, with disaster recovery plans, it can enable crisis communication as well. So bear that in mind. All right. There are disadvantages, which are all on the screen now. Usage. People will use it a lot. Setting it up, its cost is high. You have to have hardware in place. Unpredictability, security issues. Some IT member of staff has to update it, usually badly. And the client experience, feedback usually comes back that it's clunky. Internet systems are usually really easy to use because there is no opportunity for large organizations like Google to actually do training. So they have to make it so beautifully simple that you can just pick it up and it's intuitive to use. Okay. Yeah, textbooks are terrible. I agree with that. So, common contemporary applications you've got in there inside your intranet. There you go. You can also apply these to the internet as well. And we've got search engines. Search engines, this one is so random. Very random. And again, this is Eduqas for you. If it asks you about search engines, crawling, indexing, yeah, all great stuff. However, don't forget that a search engine, what is it? Typically, a piece of software has an algorithm behind it, doesn't it? It's embedded within a web page, allows the user to search for web pages or other documents. Google's algorithm for searching is so advanced that even people that work for Google struggle to understand and explain it. Think of it like an organism that has kind of advanced so far that people don't even know how it does what it does anymore. And I don't know if you've heard about this, but AI now is being built into lots of search engines to make it faster, more efficient. You can do advanced searching in search engines. You've probably never done it before. However, that link at the bottom when you've got the slides takes you through some advanced searches. So if I just type in computer science, it will just give me all the resources for those 2 words. If I said computer and science, it's another way to find resources that contains both of the words. So the search must contain the computer and the science. Computer hyphen science finds resources that contain computer but not science. Computer not science also finds resources that contain computer but not science. Just a different way of saying the one above. And also, if you put speech marks around it, finds resources that contain the phrase computer science together. And if I put compute and I put a asterisk like we've seen from our regular expressions, our SQL, it's a wildcard, so it means all, doesn't it? So it says find computer, computers, computing, computes, computed. Okay. And off we go. And that's it. That's the end of that one. Let's check what we've done. Expert systems, weather forecasting, different types of software. 3 down. 3 down. Everyone good so far? 3 down? Yeah, that's right. Good, excellent. Well done, people. We are doing well.
And like a lot of us are really smart. I'm really smart.
A lot of us are really smart. What's next? What do people want? What do people want? Shout it out. Shout it out. Where are we going next? I'll pause as people decide what they want. Why do you have a Steam Deck? I don't have a Steam Deck. I know. I do not have one. I would like one. If somebody wants to donate one to me, or donate, I'll just, no, I'm joking, don't. Operating systems, scheduling, truncation, rounding, binary, two complement. Oh, okay, operating systems. Right, okay. Let's do operating systems first, and then let's hit the binary up. Sounds good? Let's do that. Where are we going? Go back. Right, operating systems. Oh, man, operating systems. Right, there you go. See that little diagram? Craig can sell me one. Right. Do you see that? You see that? That's what they can ask you about operating systems. That diagram kind of shows you the branches. So what I want you to do is I want you to think about this, people. I won't even go through some of these because, I mean, if you can't do them, you should really know what they are. Utility software, right? Utility software, if you talk about that, you've got antivirus, compression, debuggers, screensavers, system monitors. They are the things that help your system operate. They can be downloaded, small pieces of software. They're not always default. You don't have to download them. Interface is how you interact with the operating system. So right now, I'm interfacing with my Windows operating system. Yes, I'm on Windows. Processes. So the processes, you've got interrupts, scheduling, but in addition to that as well, you've got spooling. You've got buffering down at the bottom because you've got resources. Now, when we talk about operating system resources, we split it into 3 parts: peripherals, memory, and backing store. Now, the operating system manages 2 types of memory. You've got partitioning, which is looking at primary and secondary memory. And you've got buffering, small memory modules inside devices like your printer that spits out paper. Right, that's a printer, by the way. All right, so let's go from there. Let's see where we go. This is quite large, this unit, I think. Okay. Have a read of that quickly. Peripherals, drivers, communication, memory, partitioning, buffering, random access memory. You've got backing store. Your backing store is your secondary storage. So inside your hard disk drive or solid state drive, you've got file organization and different file allocation tables. So a FAT, which stands for file allocation table, or modern people have NTFS, new technology file systems. Memory sticks have them. M.2 solid state memory in your computer has them if you've got a fancy computer. File permissions. So random. Eduqas, why do you do it? File permissions. Read only, hidden file, system files. That came up once. So, these slides are great. I'm so good at making stuff like that there. Operating systems manage peripheral devices, input and output devices. It controls the sending and receiving of data. To achieve this, the operating system uses a program called a device driver. Anything you install on your computer needs a driver, doesn't it? Sometimes you have default system drivers. That's why you can plug and play devices. Check you out. There you go. Using device drivers brings two advantages. Any device can be used with the operating system, providing it's got a driver created for it. Who makes the drivers? The people that make the hardware. So if I had a Steam Deck, I'd have some Steam Deck software created by the Steam Deck people, and I could download it, install it, all that good stuff. All right. If anyone got an NVIDIA graphics card out there, NVIDIA, you bunch of melons. If they're listening, sponsor me, right? But NVIDIA, I'm forever installing device drivers, forever. Seems like there's a device driver every week for NVIDIA. You need to chill out, guys. As for memory, the operating system manages memory mainly, the partitioning of secondary storage, allocation of data into buffers, for interrupt service routines, and the allocation of data in and out of RAM. Computer memory must be managed to ensure that more than one program can run at one time, multitasking. More than one document can be opened up at the same time, multitasking. And when a program is run and loaded into memory, the operating system determines how much memory the program requires and allocate enough pages. When we talk about pages, we're talking about blocks of memory. Blocks of memory inside random access memory. So those people that talked about pages and segmentation before, you were talking about random access memory in blocks. When the program is closed, the allocated pages are freed up for use by another program. For our backing store, managing our backing store allows us to create, modify and delete files and folders. It keeps our folder hierarchy, such as our grandparent, our parent and our child folders. So you know when you got a folder in a folder, they call that, what do they call it? I can't remember. Grandfather rights. Yeah, grandfather rights. So who's got the root folder with folders inside folders inside folders? Children of children of children. You can rename files and folders, sort items into different orders, ascending by alphabetical, or sorting it by its type. And you can restore deleted files as well from things like your bin. File permissions. Yeah, someone with read-only permissions may only be able to see it. So when I was a kid, I was a 13-year-old, and I set up the family computer. I give my parents read-only access, and I had full right access, so I could do what I want. They didn't have a clue. They're not smart enough. They didn't understand anything. I had full power and full control from an early age. It's gone to my head, I think. All right. System software. It's a type of computer program that is designed to run computers' hardware and application programs. System software is essential in order to perform even the most basic tasks. The two most common types of system software are the operating system and the system startup software. You're going to need them, aren't you, to work in tandem. Startup software first, and it hands over to the operating system. All right. If we think of the computer system as a layered model, the system software is the interface between the hardware and the user applications. Now, for utility software, system software is supported by utility software. Utility software is a type of system software which is used to support the computer infrastructure. Now, all those on your screen we talked about before, we had them on the screen. That sounds like serial killers activating events, not gonna lie. Well, you know, who knows? If you wanted to look at these later on, I'm not gonna go through those utility softwares. I hope they ask a big question on that. That'd be really nice, wouldn't it, if we had the utility software? You got to think about advantages and disadvantages of all these things. So when it comes to HCI, my fear is that you see a question in your exam that says HCI in it and you don't know what that means. Okay? HCI is what we look at. So right now you're looking at your graphic user interface. How do you as a human interact with what's on your screen? You do it through a graphic user interface, don't you? It's very intuitive. I've seen a 3-year-old like put in a PIN code and unlock an iPad and install like apps and stuff. Scary. This is the world. You were the generation that grew up with the technology from an early age. So you're basically a case study to see how you turned out. So good luck, everybody. With a good graphic user interface, you don't need to memorize anything. Nothing at all. Help facilities are on hand. Lots of information to guide you through the processes. But there are high requirements in terms of hardware. So you've got lots of memory being used with graphics. Experienced users can be slowed down by it. I've seen a load of computer nerds using command line and it's freaky. It's extremely scary. Minimal hardware requirements with command line interfaces because it's just text. If you wanted to go and have a look, go and Google right now. Google MS-DOS. It's the first experience I had of command line interfaces. MS-DOS. Thank you, Bill. Bill quickly realised that it was a bad idea to have a command line and he moved on. Good idea, Bill. Good idea. Move on. So, there was a 10 marker. Might have been 2017, 2018. And the modes, it came up, the last mark, I think it was a 10 mark question or 9 mark question at the end. It said modes of operation. Can anyone tell me, give me an example of a mode of operation? Throwing it out there now in the chat. Does anybody know what is a mode of operation? Anybody know? Not multi-user, no. Batch is one of them. That's a great start. Well done. Batch is one of them. Oh, what? RRT, BP. What? Real-time control processing. Correct. RRT. What's RRT? What are you talking about? Yeah, most of you are right. So flying through modes of operation, it came up and it was a 10 marker and they all got out of the exam and they were like, oh my God, John, what was that? What is modes of operation? I told them what it was. I said, oh, batch processing. Anybody? Batch processing? Oh, wait, auto-corrected. Oh, yeah, I see you backtracking. Right, so, batch recap. Master and transaction files are used. We have a large number of similar tasks or jobs. And they can be run with no user interface. That's great, isn't it? No user interface. So gone are the days of somebody manually making bills for people. So it's able to run out of hours, which means there's no sort of heavy impact on our our network and what we do in our hardware. So people can get on with their day-to-day jobs and run this in the evening out of hours. Then we've got real-time operating systems. Real-time operating systems refer to what we were talking about before. Usually, real-time operating systems are used with risk-to-life systems because real-time operating systems must respond in an extremely short amount of time, and you would not expect to run real-time operating systems on desktop PCs because they are unpredictable. They crash too often, and people use them. So these are systems that have their own system, and they're usually mainframe computers, large, heavy processing computers. But no matter how good the operating system is, a web page could not load in real time because of the broadband bottleneck connections. So real-time systems are never online. Real-time operating systems run only on very specific, usually mission-critical or risk-to-life systems, as I just said before. Okay, so that's real-time operating systems. You also have real-time control. Real-time control actually make effects happen when you receive inputs. So it could be things like temperature monitoring in a greenhouse. The greenhouse gets too hot, the windows open. The greenhouse gets too cold, the windows shut, the heating turns on. Right? They are continuously monitoring every single day, every single second, every single nanosecond of a day. They are continually monitoring what's going on. Inputs are processed immediately and the output is adjusted accordingly. We could never do that. We could never be on 24 hours a day to monitor a system because we fall asleep, we get tired, we get a bit blurred in our vision every now and again. Okay? And accidents tend to be avoided because we use real-time control processing. The whole system's automated with very few operatives monitoring it, and jobs can wait on a queue until they are processed. So if you think about real-time control, separate this now in your mind from real-time transaction. So I want you to think control is about time and real-time transaction is about money. So think about double booking and buying your favourite gig tickets. So if you're in Manchester, you're trying to buy Park Life tickets because you're strange and you want to go and stand in the mud listening to some horrific DJ play some outdated techno music, you be my guest. Some transaction-based systems are also considered real-time. So if one store books the last seat of a cut-price holiday, then it should no longer allow other people to book it. If it does, you've got a clash. You're probably going to have to refund people. There might be compensation involved. It's a bit of a nightmare. The transaction needs to happen fast enough to stop multiple bookings from occurring and thus considered to be real time. Now think about this for me. Could be used in theatre selling tickets, right? I'm not being brand specific here again, people. Theatre tickets, cinema tickets, that kind of stuff. When records are accessed, other users are locked out. That could be for editing. Have you ever bought a ticket from somewhere and it says you've got 15 minutes to complete the purchase? After that 15 minutes, if you've not completed it, it goes back onto general sale. The record is updated immediately and it avoids double booking. Okay? So far, in operating systems, look what we've covered. Let's jump through these. Libraries. Explain libraries. How can you use libraries? You mean like library systems? Like books and stuff? You're not talking like libraries as in programming libraries, are you? What are you thinking? Waiting for a response. Yeah, libraries. Okay, yeah, libraries are fine. Booking books, etc. So single user operating systems. One user, one time. One user has full control of system resources. Everybody else is not able to access them. Every person's got their own home directories. And that's it. It's the most simple type of user on an operating system. Multi-user operating systems allow users to log in remotely. Each user has their own visual display unit or screen, and multiple people can log in at the same time. They have their own version of their own operating system that they see, and that's it. You have to have a server for this, so it has to be a client-server network where you've got client machines and a big server in between. Okay. Multi-user operating systems, devices will connect remotely to the server and run applications there. A number of different technologies have to be employed, including a secure shell or a virtual desktop infrastructure. So a virtual machine, if you remember me talking about those in a previous lesson. They're easy to control in one location because one administrator of a server can update everything centrally. My college should go with this. Don't know why they don't. Multitasking operating systems. They swap applications in and out of the CPU extremely quickly, and that gives the illusion that they're running in parallel. So that happens quite often. Computers are serial machines in their nature, so they can only process one thing at one time, but if you do it extremely quickly, it looks like you're doing it at the same time. So yeah, that's what you use them for. You've got multi-programming operating systems. Multi-programming operating systems store more than one job in the computer's main memory. That's random access memory, main memory, at the same time. These jobs appear to be processed by the computer's CPU simultaneously. And that's good because multi-programming utilities by the CPU prevents it from being idle. So we keep the CPU running all of the time. That's getting the full use out the operating system. It gets the full use out your processor. If your CPU sits idle, that's the worst case scenario. Now, the operating system, it might move jobs in and out of CPU very quickly. However, each job gets a predetermined time slice. So that's the whole of the processor gets a slice, like a pizza. You slice it up, you give someone a slice of it, that's their processing time. So when I refer to this in class, I talk about health and social care, computer science, physics, right? Physics, they might need a bigger time slice because they might be computing certain experiments. Computer science, programming, they might need a bigger time slice because it's computer science. Health and social care, they just use browsers, they just type stuff online, they don't need it. So they get a smaller time slice. And that's how it works. Okay. Flying through this, can anybody tell me what an interrupt is? I'll leave that for you in the chat. What is an interrupt? Anybody know? An interrupt in operating system standards. What is an interrupt? Okay, stops the computer doing a task it currently was, for example, turning off the computer. All right, excellent. Let's go through this then. So, interrupts, if you think about the dinner party example that I always bang on about, right? It's very important because it explains everything. So what happens in a dinner party is people want canapes, little starters, okay? Instead of everybody being serviced one by one by the waiter, and says, would you like a canapé? 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 People say yes or no, yes or no, yes or no. That will take ages. Instead, it's better for the waiter to wander around the room and people basically raise their hand or grab the attention or the eye of the waiter. The waiter comes over, offers you a canapé, you eat your canapé. So it's basically on demand. So you're right, Christina, in the fact that it is a signal generated by a device which causes a break in the execution of the current routine. So what it does is it sends an interrupt service routine to the operating system and it triggers a break. So the CPU is working. Our device or a key press, a mouse press, keyboard, etc. runs some special operating system code to say we've got an interrupt. The state of whatever's on the CPU is put on a stack. Remember that data structure? A stack? Stacks keep the order. They are first in, last out, or last in, first out. So it keeps the order of which things have been processed in. So the state goes on the stack and we run what we need to do because it's got a high priority. And then once it's finished, we pop off the stack our previous task and continue working on that like nothing happened. And there's a diagram that explains it. So in your exam, let me give you some examples of common interrupts. Things like hard drives being ready for more data to save or it's got a request to retrieve the data. Timer interrupts, like screensavers, timeouts, key has been pressed, keyboard or mouse, peripheral devices require more data, printers, that kind of stuff, and the on and off button has been pressed. So the on and off button has a really high priority. Sometimes your operating system can refuse interrupts to happen. Okay? They can refuse it. Operating systems determine what should and should not be ran on the CPU. Now, when we talk about buffers, this is a separate piece of memory. Buffers are normally found on the device itself, so they're a small piece of memory in the device itself. And what happens is you press a keyboard, and you press the key, your computer's busy. Computer says no. What do you do then? So if the computer can't actually run what you're supposed to do, you press the key. Your computer doesn't want to lose that. So in your keyboard, it stores the key press in a buffer. Then what happens is the operating system might be ready or might not be ready to deal with a keyboard stroke, but it's already in the buffer, so we're safe. If you keep pressing your key on your keyboard now, it will beep. It'll cause a beep to happen. That might be a sticky key beep. But basically, the interrupt is caused by you pressing it, but the buffer saves things if your interrupt cannot be serviced. Now, it's important to point out here that specific buffering algorithms are used to deal with buffers and interrupts when saving data to a slower device. So the process happens where a chunk of data is sent by the CPU to the device and it's stored on a buffer. The device will slowly save the data while the CPU is free to do other tasks, and the buffer is empty, an interrupt is created and sent to the CPU, and at the start of the next clock cycle, the interrupt is then processed by informing the operating system to do it. More data is sent to the device and the cycle repeats. So it's a continual cycle of filling the buffer, emptying the buffer, filling the buffer, emptying the buffer. Now we're talking about double buffers. Hopefully you get the joke there. Double buffer, no? So double buffering happens where one buffer fills up. So one is for data and the second buffer is for processing. So as one's filling up, one's being processed. As one's filling up, one's being processed. And you got to think of it in terms of like a glass. One glass is being filled with data, and then one glass is being drank and the data's going down. All right? So when you deal with priorities, when you deal with interrupts, priority is important. And what I say, okay, if an interrupt has occurred, then what we do is we check the priority of the current running process and the interrupt itself. If the interrupt priority is greater than the current process that's on the CPU, then we swap it. Put it on a stack, we swap it. That's it. Then, if the interrupt priority is less than what's being executed on the CPU, then we continue executing what's on the CPU and we put it in a buffer. Okay, priority is important. The highest priority things get the time of the CPU first. And if you're wondering why the king is on the screen, that's because he has the highest priority. So if there was one ambulance in the country and the king had a problem, medical problem, and everybody else had a medical problem, guess what? Tough. The king's getting the ambulance. Highest priority. Now what happens if you get asked about spooling? Spooling. A spool is similar to a buffer in the way it works, because it holds the jobs for a device until the device is ready to accept the job. It considers secondary storage as a huge buffer, which can store as many jobs for the device till the output devices are ready to accept them. Spooling is more efficient than buffering, as spooling can overlap processes 2 jobs at a time. So what I think, the way I remember this in my exam was, if I print to a printer, I can basically shut my computer down after I've sent it, and it's still not printed out of the printer immediately because there's other jobs going on, but it's stored in the queue. So once everybody else's jobs have been printed, I will then print it. Excellent. Okay, memory management. Key design goal for memory management is to allocate enough memory into random access memory so that each process can run. Your random access memory has a limited space. Do we all agree? Great. Thank you for your feedback. I can hear you all. You split the memory up so that processes can be allocated more efficiently. And the process of splitting up data in RAM is called paging and segmentation. We're also ensuring security so that other processes cannot access each other's data. And we allow efficient storing of memory. And we extend memory by using virtual memory. And as I go forward, can anybody tell me what virtual memory is in the chat? The memory manager splits up RAM, random access memory, into workable chunks of storage. Okay, normally when they split into chunks of storage, they're called pages. Said that before. We know what RAM holds: operating system, functions and processes, currently running programs, current files and data you're working on, and memory addresses. So here is memory loaded with 4 programs. Thank you very much, people. Yes, you are correct. Virtual memory is when the secondary storage device is used as RAM. That is dreadful. You've probably never used virtual memory because how much RAM do you have on your computer? I wonder. You can answer that in the chat as well. How much RAM have you got? And I'll tell you how much RAM my first computer had. So there's random access memory with 4 programs. You can see that program C actually gets processed and released. And now E comes along. And you might say, yeah, we can get E in there, but we have to split it up. Okay? We have to split it up. But that might mean you splitting up and slicing up code, which is very dangerous. Don't want to split up code if we can help it. So there's 2 strategies to fix this. One, you can turn everything into pages. So option 1 is paging, where the memory is divided up into smaller sections, all of the same size, and each program is split up into a different number of pages. The problem with that is that the pages don't know what the instructions are actually doing, so we could end up separating code within a loop. Oh dear. So what's the better solution then if we're not using paging? Segmentation. Segmentation is logical. And if you don't use the word logical, I'm going to find you. I will request your paper and I will hunt you down. And you can explain to me why you didn't use the word logical when we're dealing with segmentation. So it keeps logical divisions of the program together instead of having fixed page sizes. And what that means is you've got no more breaking of loops. And it means the size of segments can vary because they do split and break down, but only in logical chunks. Okay? So you can see there that program A has 3 blocks, B has 3 blocks, but E has 2 and D has 2, so it's varied in its size, isn't it? And you just explained to me, didn't you, what virtual memory was? So if we can't split things up, we will use virtual memory. And we have a process there called disk thrashing, and that is when you're using virtual memory and your processor requests information and it goes all the way back to secondary storage and all the way back to your processor. Awful. Nitro Seeker, good to see you. Is there any way this PowerPoint could be made available for everyone as not a member? Oh, someone can I'm sure one of my students could pop my email in the chat for you. All you got to do is email that and your wishes will be answered. Now, there's a summary for you for paging segmentation. It's quite nice that. That's a mark scheme definition there from an old exam board question. Moving on to the main bits. They asked about scheduling in last year's exam paper. So I don't think it's going to come up again, but it is connected to other stuff. So just remember for me that scheduling is the term the operating system uses to define how and when a process is swapped in and out the CPU. Scheduling. Don't get confused. I don't know why this happens, but don't get confused with interrupts. I don't know why students do it. Okay, don't know why. but they do. So, when we schedule, think about 3 process states. Does anybody know the 3 process states that we've got? Let's check it. Let's check if you know, if you've done your revision. Process states, 3 of them. Thank you very much. My email is in the chat. DCRE, well done. That is great work. Oh, they know. Now, running is the first process state. If you're trying to open this PowerPoint, I send this out as a PDF, so it should open up. You need to make sure you've got PDF installed, Adobe PDF, something like that. Don't open the presentation itself in Google Slides. The PDF is the best way to go. All right, it's all the links work, etc. It's all that. All right. Running, ready to run, and blocked. They are the 3 process states. So when it's in a running state in your CPU, then everything is running. Off it goes. It's happily going, producing, executing programs. Then you've got a queue waiting around to basically get ready to run. So here is a diagram. I'll select this pen for a second. The processor gets loaded into memory. It sits in the ready state, right? Now remember, this is a queue, right? But it's not just any queue, it is a priority queue, right? Priority queue. That means that if something comes in with a higher priority, it can be moved around. What happens then? From the priority queue, it goes into a running state. Running, this is where the CPU kicks in. CPU. Then, the CPU itself, whatever's running on the CPU, if it requires input or output from the user, it will be put into the block state. So that allows the processor to get on with other tasks while we're waiting for you, the user, to put stuff in. Then after that, if input and output occurs, it'll have to go back to the queue to be placed basically at the front because it's probably got a high priority. The processor will continue running no matter what. If your process finishes and it's done, then the process dies and we load the next one in. So there's your 3 process states. Okay, so in your ready to run queue, that's what happens. I told you it's priority based. That's all in the slides for you. Happy days. Inside the running queue, this process will be given to a certain amount of time to run. So again, time slicing, people. So time slicing is the amount of time given on the processor to each job. A running process has a number of options while running. It can either complete the task and close, be interrupted by the schedule and kicked off and put on a stack. It can become blocked, waiting for input or output, or it can give up its CPU time. So that's the running state. If it's in the blocked state, that's just waiting for something external to provide the data. That's all. And we say that it's blocked. It's not bad. It's just waiting for something else to use. That's all. Okay? So time slicing. I've said this already. Time slicing runs in a round robin-like fashion. So executes one part of the process, gives up time, moves to the next one, says what process needs to be done now, gives up time for that, moves on to the next one, which one gives up time for that, and then on to the last one, and it keeps going. You can have as many, time slicing can split as small as it wants to. So if you've got 1 million jobs, it will do 1 million time slices. If you've got 5 jobs, it will do 5 time slices. And it will keep doing that until processes finish, which can be quite clunky, especially if you've got loads of tasks opening. Okay. You've also got polling. I hope you've all registered to vote, if you're 18, in the general election. But polling, there's a polling station. Polling is when you ask a question. That's what we need to remember. Okay? So this takes place during synchronous activity, so things that happen at the same time. That is a process will block until an activity is completed. So if a process is synchronous, then you poll the device by asking for its status. So you go to the printer or your hard drive and you say, are you ready to send me data? Are you not ready to send me data? Then you loop until the device responds with a ready status. So you basically just keep asking and saying, are you ready? Are you ready now? Are you ready now? Are you ready? Are you ready now? What about now? Are you ready? No? Yes? No? Ready? 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 Ready or not? Ready? Ready? Until you get a ready return and you carry on with your life. Okay? That is called busy wait polling. So as long as you can describe what polling is, they normally put polling, time slicing and threading all together. So what is threading? You've probably heard of threads when it comes to parallel processing. Okay? Threading is where processes split itself up into mini processes known as threads. Each thread will be managed by the scheduler separately, meaning that they could be running in different order. So in a multi-processor system, you've got lots of processes running lots of different threads across the whole machine. That might be one process that needs doing, but they get split up into mini sub-processes called threads, and they get spread out. Okay? As the thread is under the control of the scheduler, it can take advantage of multiple cores because the scheduler decides where things go and who processes what. The problem with threading is that you have synchronization issues when you're trying to put everything back together. It's annoying. Programming a multi-threaded environment is very challenging and very difficult. And each thread can access the same data, which could cause changes to happen and unintended effects, and it's very, very difficult to test for that. So two threads that are running on separate cores, what normally happens is one that's using the data will lock, and then the other process that wants the data can't access it until the other one unlocks, and that's called a mutex lock. It stops things accessing other things elsewhere while they're being used, because that can cause weird errors. We don't like that. Okay? Right. There we are. Operating systems. Oh my goodness, I have dry mouth. So, I'll tell you what I'm going to do, people. I'm going to have 4 minutes as a break. I'm going to give you 4 minutes to go and have a rest break, relax, stretch your legs, stretch your eyes, your ears, your nose, head, shoulders, knees and toes, whatever. Right? Relax yourself. Back in 4 minutes, people. Don't worry.
And we say bye-bye.
And like
And we
a
say
lot of us are
bye-bye.
really smart. I'm really smart.
Oh, we're back, people. We are back. Oh, yes. Let's go. Right. Anybody want some binary? Anyone want binary? Anybody? You better believe it. Here we go. Right, you know what I'll do? How about we have a go at some exam questions then? Because there's no better way to learn than through exam questions, is there, I suppose? Hopefully you're all still there. Maybe not. Some people fell asleep. Whoop. Let's go this way. Right, let's jump to some exam questions. This one is an assembly language question that we can have a look at. We have some SQL database questions. Hopefully you've absolutely nailed SQL, because it is a dream boat when you can just sit there confidently, smugly creating wonderful answers. Binary. Ooh. This one's from Majid. Okay, so we've got shifting down here. Shifting. So the first question in here, if I just get this. Ooh. Right, so we've got to convert hexadecimal numbers B16 and B16 and 19. Anyone know what the 16 stands for? B6. So these little things under here. I've lost my pen. That's what I'm struggling with. I can't find my pen. There we go. Right, so hexadecimal. So this is in base 16. Now, one thing I will warn you about is stuff like this. So when you've got like, don't be starting with me. Right, when you have something like that in the exam, people go, oh, look at that, it's 34. No, it's not 34, it's 3 and 4. You've got to be really careful. Now, this 4-mark question splits this down into parts. So apologies if you know hexadecimal and you're happy with it. But hexadecimal goes 1, 2, 9, and then A, 2, F. It's represented using 4 bits, which is basically classed as a nibble. So, for example, if I put down here 9 in base 16, I would look and say, right, it says there 2 8-bit binary numbers. That is what people really struggled with. I just said it's in nibbles. So if I said to you, well, all right, 1, 2, 4, and 8, they are. That's 4 bits. What's 9? There you go. That's 9, isn't it? Now it wants 8 bits. So all right, I'll just give you 8 bits then. Look at that. It makes no difference, does it? 16, 32, 64, 128. Yeah. That is now in 8 bits. So if I did B as well, what's B? If A is 10, B is 11. If I wanted 11, can I represent 11 using 4 bits? Well, 8, 0, 1, that's 10, isn't it? And 1, that's 11. Yeah, job done. Easy. Don't mug me off, yeah? Now, it says calculate using binary addition. Binary addition, no problem. So 1 and 1, what happens when you get a 1 and a 1? Well, that's 0, isn't it? Carry a 1. So I've done that. Then I've got a 0 here and a 1 there. So 0, 1 and 1, it's just the same as the previous one. 1 and 1 is 0, carry the 1. So I've got 1 there and 1 there, which is 0, and carry the 1. Now you need to make sure you write your carry bits down, because your carry bits will get you a mark for this question. Cannot stress that enough, people. Now, the next one there, you've got 0 and 0. If you have 0, 0 and 1, that equals 1. Then you've got a 1 and a 1, which is 0, carry the 1. You've got 0, 0 again, and that is 1, because it's 0, 0 plus the carried bit, which is just 1. And then all of these here are 0, 0. How many was there? That's 4, 5, 6, 7, 8. And they're all zeros. Okay. So I've got 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0. Is that what I got? Okay. 0, 0, 0, 1, 0, 1, 0, 0. I thought I was going mad then for a second. Now, the last part, when students have done the binary addition, they don't read the last bit because look what it says. It says calculate using binary addition the total that would result from the adding of the two binary numbers. You must show all of your working. Well, I've done the first part. Part 1 is up there. I've done part 2. I've done the addition down here. Now I have to show the result of this. So 0, 0, 1, 0, 1, 0, 0, 0. Well, it's 128, isn't it? 64, 32, 16, 8, 4. Oh, well, I've done 8 again. What an idiot. Right, 16 and 4. And that's it. Okay, add them together. Hey, presto. And the final answer is 20. All right with that? Nice and straightforward, but you've got to do all of it. Show the result. After this one now, this one says copy the table below into your answer booklet, complete the table, and demonstrate the effect of carrying out an arithmetic shift. Write 2 places on the 8-bit binary representation of 2's complement of negative 44. Now then, what you've got to do here is you've got to be really careful. Let me just get rid of all the ink on this slide. What I'm going to do, I need to go back. Okay, I was looking for a little house so I can get back. Okay, now what I'm going to do is I'm going to run through the 2 different types of shift that come up. So I'll just click it here. Floating point form, let's get down there. What? Right, here we are. Mohid asked for truncation and rounding, right? So nice and quickly, I know I'm going a little bit off topic because we're going to go back to that exam question in just a second, but I want to give you the theoretical side of it first before we tackle the exam question. Okay? Do that first. Truncation. What is it? You use it all the time in maths. You do rounding normally in mathematics, don't you? So rounding is when our standard rule is we look at a number. If it's 5, then we round up to the next nearest number. That's usually the rule. Computer science, binary, it works a little bit differently. So it says there, describe truncation and rounding and explain their effect upon accuracy. It's usually always along the lines of those questions. So, for example, 8-bit numbers 0.010101 to the subscript 2, that's binary, could be stored in 4 bits as 0.010. It's true, it could be stored as that, couldn't it? Right? And what does that mean? As we do that, what are we doing? We are slicing off 4 digits and we're basically ignoring these digits here. Okay? Now what you might get asked is when you get asked to explain their effect upon accuracy, you have to produce 2 things. One is the absolute error. Now the absolute error is the original number, which is 0.0101101, minus the truncated number, which is 0.010. The best way to do this is to, instead of doing binary subtraction, is just convert the numbers. Remember, you got to calculate in the exam, remember, haven't you? Calculate it and then just minus it. That's it. And what you'll get, if you do this one, you'll get 0.1015625 in base 10 because I converted the numbers into denary. Okay? Then, that's the absolute error. But you're not done there. You're not done yet. Then, you work out the relative error. The relative error is the absolute error, so the result of this, which is this one here, So you take the absolute error, and then you also take the original number in base 10. Okay, very important. The absolute error, which is already in base 10, and the original number, which is base 2 there, but I would convert it into base 10, and then I would divide it this time. So relative is division, absolute is minus, and that would get me 0.288888889. Okay? Which is basically, when converted to a percentage, is 28.9. That is the degree in which it's accurate or not. Okay? And you'll see what I mean in a minute when we compare it. Truncation, when we compare it to rounding. So remember that number, 28.9. So moving forward, rounding. Rounding is what you're used to, because truncation is just chopping the number off, whereas rounding has a little bit more logic applied to it. Okay? So, for example, my number is 0.0101101. Could be stored in 4 bits as 0.011. Okay, after rounding. Okay, so this is a different example. Now we can calculate the same thing again, and we can say, right, absolute error again was the original number minus the rounded number this time. Now notice that the number, there's the previous slide, yeah, the number here is the same as the number here. When it's truncated, it looks like this to 4 bits. When it's rounded, it looks like this to 4 bits. That last digit there, if we chop it off like this, slice it there, if that number is a 1, then this number becomes a 1 when you are rounding. If you're truncating, it doesn't matter. You don't have to think about that at all. I'll say that again for you. If you slice it off here and this number here is a 1, then you're going to convert this left one to a 1. Now, once you've done your calculations for your original number minus your rounded number, it gives you this in base 10. This one then goes in because you've got to produce the relative error. And then you've got your original number in base 10. You do the same calculation again with the division. And this time it gives you 6.7%. So if this is 0, yeah, that is more accurate. That's the most accurate you're going to get. So 6.7 loses accuracy, but not an awful lot of accuracy compared to the truncation. So rounding is always more accurate. Whereas truncation, maybe not so. Okay? Maybe not so. Unless that last digit isn't important. Okay, but you have to prove it. So you have to do the absolute and the relative error. Okay? That was a side note there. Correct. Negatives, ignore them. So, left shift functions. Left shift here, people. All right? So, left shift functions are the same. So when we've got logical shifts, so a logical shift operation shifts each binary digit left and the vacated bits are replaced with zeros. Let me show you what we mean. Here is a number. We want to move every one of these numbers here left one. So that would be down here, down here, down here. Everything's shifting left. You understand? Now what happens when you shift left normally, the vacated bit, so this bit here that's vacated, will be filled with a 0 in a logical shift. Okay? Now usually when you left shift by 1, everything is multiplied by 2. So you do whatever number you put in, if you left shift it, you usually double it. That's what happens because it's base 2. So every time you shift left, it goes up, doubles. So if that number there, what is it? 32 plus 8 is 40, 43. 43, yeah. 43, 86. That would be 86, that now. Should be. Well, if you had 64 and 16 and 4 and 2, yeah, there you go. See? If you do 2 shifts, guess what? Doubles again. So that goes over there, 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 and there. The vacated bit moves there, and the new vacated bit, again, is filled with 0. If the number is 128, then what it does is it overflows. So if there's a 1 bit here, that overflows and goes down there. That causes a problem. So if you do see that in your exam, yeah, you will just calculate the number as normal and ignoring whatever overflows. And then the exam question would probably ask you and say, why is that number not accurate anymore? And you would say, that's binary overflow. Thank you, Dynasty Prime. Just in time. That was beautiful. That was like correlated to what I was just saying. That's amazing. Thank you. Right. Arithmetic left shifts then. Right. What do we do with these? So when an arithmetic shift, when it performs a left shift there, the vacated bit is always replaced with 0, just the same. So you might be thinking, well, what's the point in this? What's the point in this? Logical and arithmetic shifts, they do the same thing if they're moving left. All right? Now, the next bit is right shift functions, and this is where the difference comes in. So, if the question says, I would like you to perform a logical shift to the right, and the vacated bits are replaced with zeros, then this is what we do. We have our number. We have our number there above. And all we're going to do is we're going to move it. We're going to move it left. Right, and right. That was a bad line. Vacated bit, just like before. Okay? The difference now. We'd be able to... I can't see that last bit because it's my screen. Oh. See how big the number is. Yeah, we would do, because it's demonstrating that overflows happened, if that's what you mean. Arithmetic shifts, if you're shifting to the right with an arithmetic shift, then you move it to the right, but the vacated bit this time, which is called the sign bit, so remember that 128 bit also can represent positive or negative if you're doing things like 2's complement or sign of magnitude. So that sign bit needs to be a sign bit. If it wasn't a sign bit, if it was a sign bit and you change that to a 0, then you know what you're doing. You're turning it from a negative number or a positive number into a negative number or a negative to a positive. That is bad. You don't want to do that. So just remember, right arithmetic shifts, you replace the sign bit this time with whatever was vacated. So if it's a 1 leaving, then you put a 1 back in. If this was 0 here, and you vacated it and you shifted it down there, then that would also be 0. So it's a little bit smarter, and I'll just explain that one more time. When an arithmetic shift is performed to the right, the vacated sign bit is always replaced with the same value bit. If you shift a 1 out of the sign bit, you replace it with a 1. If you shift a 0 out of the sign bit, you replace it with a 0. And as some people... Would you do an arithmetic shift for 2's complement? Yes. Whatever number's provided for you, you shift it regardless. So pad with 1 or 0 if the sign bit is 1 or 0, basically. Exactly that. Exactly that. I mean, how can I explain underflow and overflow? Well, if you've got a bit that's tipped over to this side, then this is overflow. Overflow is what happens when the binary digits flow outside the register range. So if it says you've only got 8 bits, then you've only got 8 bits. You can't add any more on, it's not allowed, because that's what you've been told. The reason why they say that is because your register, your random access memory, only has a certain limit. Your CPU, if you've ever had a CPU installed, or you're a computer builder, and you've got a times 64 processor, then that means you've only got 64 bits to contend with. Now, that's a big number, isn't it? 64 bits. I mean, that's only 8, and it gets to 128, which is 255 different combinations. But 64. What about times 32? You can get a times 128 now if you're rich enough to afford one of those processors. I'm not. Like and subscribe. So they get disregarded because they're outside the register. Now, underflow. There we go. Underflow occurs when the number is too small to be represented in the given number of bits. So same thing happens. The number can't be represented accurately due to the shift. So the number is stored as 0. So it just basically just shifts down. So that number there has shifted, and we can't represent anything lower than 0.0078125 or 128th. So we just ignore it. It basically turns the number to 0, which again loses accuracy, but here's what it is. Okay. Right. Let's go back and tackle the question then now. We've got our newly found knowledge. I've not put houses on all these, so it's hard to get back home. There we go. Give me a house. Click on that one. Finally, exam question. Okay, there it is. There it is. Copy the table below in your answer booklet. Complete the table to demonstrate the effect of carrying out an arithmetic shift right of 2 places of the binary 8-bit binary representation in 2's complement of negative 44. This is a great recap for us to actually create our 2's complement. So if I do a little register down here of 1, 2, 4, 8, 16, 32, 64, 128. Have I missed one there? Have I got too many? Or have I gone too far? 1, 2, 3, 4, 5, 6, 7, 8, 9. Why does it give me 9? Anybody know why? What's going on here? Sign bit? What? What? Absolute crazy. Well, you know what? Oh my goodness. Oh my goodness. Do you know what? This is the stuff that they do that's really annoying. I'm going to do that again. So I am going to use my standard 8. You say sign bit, but the sign bit is the 128th bit. I mean, 64, 128. For overflow. Right, anyway, so what I'll do is I'll convert 44 and I will then 2's complement. Is there any other rules for 2's complement? Anybody? Anybody know the rules? I can put... Overflow later, okay. I'm waiting for the rules. I'm waiting for the rules before I do it. Actually, I'll do 44 while you give me the rules, okay? One of those. One of those. One of those. Excellent. Now, what I'm saying is, I wonder what method people are going for. There's 2 methods for 2's complement. Okay, the first method is the one I'll follow the one that you're talking about in the chat. Okay, so you basically copy from the right hand side. This is how if this was a question in my paper, this is how I would explain it explicitly. I would say, starting from the right hand side, or you could say the least significant bit, starting from the least significant bit, copy up to and including the first one. Then invert all the other bits okay. Some people will invert all the bits at once and then add a single one to the right hand side. But that method, which is allowed, that method causes so many mistakes and errors because people are doing binary addition then. However, that first method that everyone's talking about in the chat is probably the best method. So now I've got negative 44, so I might just put that in there as in 1, 1, 1, 0, 1, 0, 1, 0, 0. Okay? There is my number. Now what do we do next? What we do is we do a shift, don't we? So the right arithmetic shift, remember the rules. The reason why they ask you a right arithmetic shift is because it would be, right? But remember, Nitro Seeker. Right, this is the 9th bit. This is the weird one. Why did they give me that? That was a stupid thing, wasn't it? This is the 8th bit. This is where you'd normally go from. And I'll find the mark scheme on this because I'm pretty sure when I saw this in the mark scheme when it first came out, I'm pretty sure it had 8 boxes on the mark scheme, and it might be an Eduqas idiocy again. But I can't promise anything. But I will check the mark scheme for people, and I'll put this in the slides. I'll find the mark scheme for you, and I'll whack it in the slides so you've got the mark scheme so you can see it. But you know what happens on a arithmetic shift, don't you? We basically shift everything to the right. So if I copy this down here, that's going across there. That's going across there. That's going across there. Across there. Across there. Across there. Across there. Across there. Mohid, is Mohid still with us? 1, 1, 0, 1, 0, 1, 0. That gets destroyed. What am I going to put in this box, people? 0 or 1? 50-50 guess. What are we saying? 50-50 guess. What are we saying? Ooh. Oh my
And like
goodness.
a lot of us are really smart. I'm really smart.
Oh yeah.
And like a lot of us are really smart. I'm really smart.
That's right. Really smart people. Really smart people. 1. Come on. Right. There we go. Okay. Now, what we're going to do is we're going to shift again, shift again, shift again, shift again, shift again, shift again, shift again. Okay. And then it'll go 1, 1, 1, 0, 1, 0, 1. Wait a minute. Why did I just do that? Oh yeah, that's right. I thought I was going mad for a second then. Okay, what goes in that box there? In the sign bit. Here's our sign bit. People are going 1 again. Good. Right. That was easy, wasn't it? Now, if you don't have to do this for the exam question, but it's important for me to make you understand what actually is a signed bit using 2's complement. So hold the phone for a second. Let me just get my eraser, get rid of this. Go back to my pen. Right. In 2's complement, your number line looks slightly different, doesn't it? 1, 2, 8, also 1, 2, 4, 8, 16, 32, 64, and then it's 128. But in 2's complement, it's negative 128. So if you've got a 1 here, I'm going to take negative 128. Someone can get the calculator out and check this out. Check that I'm actually not making this up, because I'm going to do a negative addition now. If I get it wrong, it'll be embarrassing on a live stream, won't it? So negative 128 plus positive 64 plus positive 32 plus 16 positive plus a 4, that's positive, plus a 1, that's positive. And now if I go, right, so 128 plus 64, mental maths, don't fail me now, plus 16, so that's, I think that is negative 11? Has anyone checked that? Negative 11? Are you writing with a mouse? I'm not writing with a mouse. Is my writing that bad? Rude. I'll shadow ban you. Absolutely disgraceful behaviour. Okay, negative 11. So if you, let's say Negative 44. I told you before, if you shift it left, it doubles. But what happens if you shift it right? It should half, right? It should half. So negative 22, negative... Oh, look at that. 2 shifts, negative. That is how I would check my answer. Correct. Yes, Joel Oslin Roberts. That is right. Shout out on the live stream. People actually ask me for shout outs. Can you believe it? I think I've made it. No, I was wondering how you manifested to do it. Would be very impressive with mouse. Yeah, well, yeah. You know what? I'm left-handed as well. And I've had to adapt to a right-handed world. Especially with the mouse. You can get left-handed mice. But I'm not an idiot, so I can just adapt. Okay, moving swiftly on. You know what? I think if we move on from here, this is one that people struggle with. Especially people not from my college. Wait, so left is times by 2 and right is divide by... Correct, yes, yes. Or as if Maroof is here. There you go, Maroof. That's your shout out. You're actually a I was going to call you then. I was going to call you something. Won't be professional. You're a mature student. There you go. You're a hard-working student sometimes. Can I have a shout out? I don't know who you are, Bob. What about me? I don't know who you are, Dynasty Prime. What's your words? Yeah. Sorry, Maroof. I won't do it again. Okay, so this is my method. If you can't get this method down, you've never listened to me. Why have you not listened to me in class before? Probably because you're too busy messing about on your phone or something. Typical. Right, so in a certain computer system, real numbers, that's decimal point numbers, are stored in floating point form using 16 bits as shown, 16 bits in total. So we've got the mantissa. The mantissa, think of that as the value of the number. Okay? The exponent is to the power of. So to the power of 3, to the power of 3, to the power of 4, 8, whatever, to the power of. So this is basically how many places we move that decimal point. So I'll think of it as decimal movements. Okay? 12 bits. 12 bits in 2's complement form. Oh my goodness. Oh, that is scary. Now what it means is, it's basically a sign bit. It has a sign bit on it. The binary point of the mantissa is immediately after the left bit. So what it means is that one, then that's where the decimal point is. Then you have all your numbers after it, etc., etc. Okay? 4 bits, again, in 2's complement form. So that would be 1, 2, 4, and negative 8. That's what that exponent would look like. Clearly show your working, convert 65.75. 65.75. Okay? So, in the chat, can anyone tell me what 65 is in binary? As if it's Max Cooper. What an absolute legend of the computer science world now. Max Cooper, I hope you're doing well, my friend. I've kept my eye on my what do you call it? LinkedIn. Great work. You're doing great work out there. Just remember when you're rich and famous, just remember who John is, yeah? No, the reason why the thumbnails have improved is because someone called me out. Someone says, oh, your thumbnails are rubbish. Like in person. Not even online. Oh, I don't mind online trolls, but person trolls, oh my goodness. Demoralising. 0, 1. How many is that? Listen, I'm going to trust you all here. If you're wrong, I'm going to be well upset. 4, 5. Is that 5? And 1. 1, 2, 4, 8, 16, 32, 64. Okay, 64. That was easy, wasn't it? That was easy. Typing that gave me a stroke. Oh, okay. John, that's called misguided criticism. Oh, yeah. Nitro Seeker's gone one step further. He's gone for the 0.75 as well. Absolute nutter. Crazy. 0.5, 0.25. So that's one of those 0.5s and one of those 75s. Excellent. Right, that gets you a mark straight away. then what we do is the next thing now, follow me through here, people, is 4 steps. So first step is done. That's convert. No, that's convert the number using the smallest number of bits. Happy days. We've completed that. However, this isn't the smallest number of bits, is it? That is the smallest number of bits. The second step now is to normalize the number, which means because it's a positive number, it just means putting a 0 point on the front of the number. Oh man, done that wrong. One. Okay, that's now normalized. Normalized is this bit there. We'll never forget, John. Good luck to all the students. There we go. Hope, Max, they might follow in your footsteps if you actually offered some degree apprenticeship places. Okay. From here, we have 0 point there now, so it's normalised. The third step of John's 4-step method is to now calculate how many bits we've used and pad out that number to the correct number of bits for the mantissa. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits. I've got 10 bits and I need 12 bits for the mantissa. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we always pad on the right hand side. The right hand side. Okay, if you pad on the left hand side, you're doing arithmetic shifting. And we've just learned that if we put zeros on the left hand side, you're going to push the number down to the right, which means you're going to half the number every time. And you change the value of your number. So don't do that. Rohan, interview. Oh my goodness gracious me. Who give you a job interview? Crazy. Okay, now, from here, after we've done the third step, the last and final step is to work out the exponent. So the exponent is the difference between the first decimal point in the normalized position and the last decimal point. So how many do we have to travel? We have to travel 1, 2, 3, 4, 5, 6, 7 places. 7 places. What? So I'll write out my number for the final time. Getting all the marks because I'm showing my working. There's my number. And now the exponent goes on the end. So 1, 2, 4, and 8. But it's negative, isn't it? Right? So it's negative because it's 2's complement form. 0 because it's going to be a positive number. 1, 1, 1. That's 7. Right? That's positive 7. That is my number complete and my answer. So just to remind you of the 4-step process. Step 1, convert the number to binary using the smallest number of bits possible. Step 2, normalize the number by putting a 0 and a decimal point at the front of the number if it's positive. Then count the number with the normalized number on it. Count that because it counts. 0 and the 1 and the 0, 0, 0, 0, 0, 1, 1, 1, 0. And then add the zeros on the end. So this is where the padding goes. So that gets us up to the required number for the mantissa. Always normalize first, then pad, because the normalized number goes into the padding calculation. Okay? There's never been a negative number on this exam board. Bob, you won't get a question on Little Man Computer. That's just a method that we use to show you how the fetch, decode, execute cycle works. And finally, the 4th step is to convert the exponent, the exponent. which is the difference between the second decimal point and the first one that you put in during normalization. Okay? So that is how you get that answer. All right. Alrighty then. Clear it all. Now what we're going to do, this one says, in a different computer system, real numbers are stored in floating point form with an 8-bit signed mantissa, 8-bit signed, and 4-bit signed exponent. Clearly showing you're working, very important, clearly showing you're working. Calculate the decimal value of 0.110100100101. I want my chat people, can you work that out for me, please? Answers in the chat. There you go. Just want the decimal value in the chat, please. See if you can do it. You've got to reverse the process, that's all. OCR, OMR, MIR, the touch screens and what they do, yes, they're a part of input and output devices in the first chapter in hardware communication. Yep. Capacitive and resistive, yeah. System design, comp 1. I will check that in a minute because I'm pretty sure it does come up in this one, in the input devices. Ooh, Nitro Seeker, is that what you've gone for? Crazy, crazy man. Who is Nitro Seeker? Are you from my college? I don't even know if you're from my college or not. So we're going for, is that the answer we're going for? Some people not sure. Right, again, this is another area that you can mop up really easily. I've got videos of this stuff on my YouTube channel, which you can happily go back and have a go at. Comp 1 besides design, blah, 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 No, there isn't, but sometimes a little bit of crossover because they have to use other things. So things like, what was I looking at before? Oh, I was looking at hashing algorithms and hashing tables. Hashing tables are data structures, which is comp 1, but hashing algorithms are file organization. You know what I mean? So they use them structures, so they have to use it. Right. So someone gave me an answer before. Let's check if it's right. 105.32125. Okay, so you start at the right hand side because this is where the 4 bits get stripped off. 1, 2, and 4, and -8. This is so you've got an exponent of 5. An exponent of 5. So something to the power of 5. Let's have a look. We start here and we go 1, 2, 3, 4, and 5. Oh, right there. Now once you've got that decimal point in place, you will then work out that this is 0.5 this way and then 0.25 there. So I've definitely got something 0.25. Then I've got 1, 2, 4, 8, 16, and 32, which is negative because it's 2's complement. I've got 16 plus 8, giving me 24, plus the 2, 26. 26.5 is that? Oh, 26.5. You get 1 mark for calculating the exponent on that question. You get 1 mark for moving the decimal point, and then you get the final mark for actually producing that there. That was all right, wasn't it? That was all right. God, that. If you look, right, one thing I will do for you for a second, if I go back and look at that, 8A, 4 marks. 8B, 3 marks. That's 7 in total, isn't it? 7 plus C, which is, that's 10 in total. Plus D, which is 13. That's 13 marks, that. 13 marks. It was only a 3 marker, that one. What are you talking about? What's the final mark for? You big donut. What are you on about? 3 marks. 1 for the exponent, 1 for the moving of the decimal point, and 1 for the... that's the actual answer. Yeah, the actual answer itself. That's, look, mark there, look, 26.25. Answer. Okay. Okay. Oh, look at that. Look at that question there. Oh. This one. Data types. Boolean. What's a Boolean? A Boolean is a data type, isn't it? That can have two values. That's it. So it's intended to represent the values of logic. So you've got true and false, which is 0 and 1. So it represents 0 and 1, but in actual fact, it's trying to represent Boolean algebra logic, which is 0 and 1. It might be stored as a single bit. So it's the most efficient of all data structures, data types, because it is a 0 and 1, which is very small. The reason why I put this on here was because of that. You might look at that and go, what the hell is a fixed length string, John? What is a fixed length string? Does anyone know how many bits a string uses? Like A, for example. How many bits it uses? Oh, yeah, DCRE down here. So string data types is the number of characters by 1 byte for ASCII and 4 bytes for Unicode. Ooh. Now, if you're talking about ASCII, ASCII can be 8 bits, or if you went with 7 bits, you'd still get the mark for it. Whee! Extended ASCII is 8 bits, and standard ASCII is 7, or old ASCII is 7 anyway, but yeah. Whoa, Tuffajul! Reared his head. Always nice to see Tuffajul. Turns up on time for my live streams, but not my lessons. Yep, that's right. Boom. Roasted. You know what? And I think Tuffajul, that won't be the last of it either. I've got more. So, so fixed length. So you've got ASCII. So just remember, a fixed length string, it's a series of characters where the number of characters is fixed by the programmer when declaring the string as a variable. So you might say, okay, the user wants passwords that are exactly 8 characters. I don't know why it would, but it's just a random example. Okay, exactly 8 bits. So when you declare the string, you're going to say that's just 8 bits in total, which would be 8 multiplied by either 8 bits for ASCII, so 8 by 8, so 8 characters in total by 8 bits each, or you could say 8 bits by 7. If you went with Unicode, okay, that is quite a bit more. So it's 4 bytes for Unicode there. 4 bytes. Remember how much a byte is? Eight bits, isn't it? So bear that in mind, people. Bear that in mind. Yeah. I put this in here. This is an example of the stuff that I've already been through, so I won't go through it again, but compare in terms of range and accuracy, fixed point and floating point representation. That one, actually, it might be worth tackling that one. Okay, just remember, let me just tackle that top one. If you're talking about floating point, and fixed point, let's put that down as a little title. Floating point has a set number of bits. And that's for your mantissa. So you set your number of mantissa bits, and you set your number of exponent bits, and that's why they give you that in the question. Okay, set number of bits. There is a trade-off. There's a trade-off between your accuracy and the range of the number. Okay, if you increase the exponent, then you might increase the accuracy. And if you increase the mantissa, you might increase the numbers that you can use, so that might improve your range, for example. All right. But if you move the exponent, you can basically have more decimal points, which makes it more accurate. So bear that in mind. And also larger mantis. So yeah, so larger mantissa. Oh, so wait. Other way around. I'm feeling the other. Yeah, that one. That's right. That's better. Yeah, because you move the exponent, the decimal point moves down, which creates a bigger range for you because you can use more bits on the left hand side, which will give you a bigger number. Yeah, that's right. Mantissa, greater accuracy. Exponent, greater range. I'll just pause there for effect. So, it's not possible though. It's not possible to represent 0 using floating point because you have to tell us where the decimal point's going to go. So you're going to have to move the point somewhere, and you can't accurately state where that's going to go without having fixed numbers. With fixed point is not flexible. So it has a set range and level of accuracy. It's less complex because we don't have mantissa and exponents, okay, but fixed point is what it is. So it's the number you see on your screen. That's all it is. So I'll write that down. Not flexible. So you can't shift your decimal point to give you better accuracy or range on this one. Not flexible. Okay, but it is less complex. No 4-step method for fixed point numbers. Arithmetic underflow may occur when carrying out floating point operations. Describe using an example arithmetic underflow. So that if you wanted the answer to that one, all I would say is 3 marks. The command word is describe. So it occurs when the result of the floating point calculation is smaller than what the computer can represent in memory. So we're trying to move it down so far, but our memory doesn't go down that far. So realistically, what needs to happen is it needs to be rounded or truncated so that you can actually display the number. And if you provided a suitable example like I did earlier in the stream, then you could see that. I've got a couple of others as well, which I put mark schemes to these ones because they're quite wordy questions. These are the expert system questions that are up there. And one thing I wanted to show you finally, because I think I'll call it a day in the next 5 minutes. These are the final questions from 2020 all the way to 2023. Just have a look at them for a second. Does anybody notice anything about these questions that is the same? I'll say that again for you. Does anybody notice anything about these questions that is the same? They're all 9 marks. Thank you, Bob. He's found the easiest thing to comment on. Anybody else? Anybody else? Well, yep. They're all 9 marks. We know this now. Fairly open-ended, so you can draw on your own. They are, when it says you should draw on your knowledge, skills, understanding for a number of areas across your computer science course, that opens up the mark scheme so you can say anything you want. They're all using Eduqas, sycophantish discussion, or explain. Okay. So, doesn't Welsh 30 mark and final question? Yes, it does. But it doesn't matter if it's a 9 or 13 mark because the process is the same. Remember, 1, always relate to the question, provide facts. You've got to provide the content that would come across from the specification. Then, you then start using your computer science nuance, your technical terminology, and your own opinion based solely on fact to come up with these... I'll come to answer these questions. So, explain, giving an example of each. What is meant by the concepts big data, data mining, and predictive analytics? So that's 3 areas that you're going to talk about. You divide that into the 9 marks. All right? So what is meant? So you have to give examples of each one. If you're not giving examples of each one, then you're never going to access any banding on that. Okay? The second one in there, the weird thing about 2020, they had 2 9 markers one after another, which is pretty, like, just makes me want to vomit. Why would you do that? 2 9 markers. At least throw a couple of low stake questions in between. I don't know why they did that. It seemed pretty stupid, but less said about that, the better. Describe the purpose of an operating system in a personal computer. How broad is that question? Maybe they do it on purpose. Maybe they do it to allow you to talk about absolutely anything you want. But when I showed you that diagram before of an operating system, which had loads of different parts like utility software, and it had memory management, and it had your sort of process states, and it was talking about spooling, and it was talking about polling and threading and all that, right? Again, that's what you would add into that 9 mark question, okay? 2021, a cyber attack is an attempt to damage, disrupt, or gain unauthorized access. Yeah, well, that's a fact. That's what they started with, a fact there. Then discuss the implementations, okay? So just look there. I'm hoping that you're seeing some of this here, because it says, give examples in the first one. Then it says, describe the purpose. Then the next one says, just discuss the implications. And then the one below that, discuss the contingency planning that a business should carry out to enable them to recover from computer system disasters. So they're kind of prompting you to go down certain alleyways with this stuff, but you've got to talk about the area on the specification that they're referring to. If you start to get in 2022 and 2023, if they start to open it up a little bit, then you can kind of draw other parts of the specification in towards it. Discuss contingency planning that a business should carry out to enable them to recover. So what would that be? That would be things like redundant servers. They could have contingency planning, so they could have people off-site. They could store things with backups and things like that. With partitioning of main memory, 2023, that was by far the worst question that I've seen for students. Not many of them like that at all. Partitioning main memory. Pretty harsh. Okay. Do you have any strategies to answer those massive questions? Yes, I do. You got to break it down into parts. So the first part, I would go and I'd talk about the subject matter and give the facts. So if I was talking about contingency planning, I'd talk about what is contingency planning, how can we do contingency planning, and then in the second part, I would refer it to the question. So with the facts, then I apply my knowledge, because facts are very like low band. Just give me the facts. The second part, apply your knowledge. So this is talking about a business. So how would contingency planning save the business? So now I'm going to start talking about the revenue, keeping systems online, allowing staff to work all the time to maintain the business as it is. So people don't really know that there's issues with the business and a disaster's happened, we can maintain our productivity levels. So now I'm relating it to the question. That's the second part. And the last part, I would give my conclusion, my opinion, my final discuss contingency planning that businesses should carry out. So I will say they should be doing this. They should be doing that. So it's my opinion. I think they should be doing that. I think they should be doing this. Right? That's how I would do it. Just 3 simple parts: facts, knowledge, conclusion, opinion. That's it. 9 marks in the bag. You know you're going to get one. And when you open your paper, it's 2 hours and 45 minutes, and you do not need 2 hours and 45 minutes for this paper. If you do, you need to pace yourself a little bit better. But flick over to the 9 mark question first, have a look at it, and then as you go through the paper, your brain will have a little bit of time to process what that's about. Because if you just look at it straight away in the last question and go, 9 marker on this, right, okay, I'll start writing. No, do not do that. Plan out what you're going to do. Algorithm in mnemonics. What are you talking about? Are you talking about assembly language there? That's what you're talking about? It's finishing. No, it's not. But you've got plenty of time, so I wouldn't rush it. really, I write on the side of the papers. I would expect normally it takes around the 2-hour mark. That's usually where students are at on that. That's right. Okay. All right. Does anyone want me to actually do assembly language while we're here? Have a look at this kind of question, something like this. This will probably be the last question of the evening, I suppose. 2.5 hours of unpaid time. Do you have to know all the commands? Okay. In these questions, what they normally do, dynasty prime X. What they normally do, they normally give you the table. They normally tell you what to do. Okay, so the assembly language commands are normally provided, and it provides a description of it. So as I go through this question, it says, in a typical holiday apartment, let me just adjust my microphone because it's on a screen up here. I want to make sure you hear me. Okay, there we go. In a typical holiday apartment, the air conditioning system is set to regulate the temperature at 21 degrees. If the temperature rises above the required temperature, the system will be switched on to the lower temperature. A control program for the air conditioning system is to be written in assembly language. The acceptable temperature is stored in memory location num1. So it's provided us with a variable called num1. So you know that num1 is going to store some information for us, and there it is. So that's quite helpful. The required algorithm is loop continuously, right? So as I think about this, whenever you see a loop, right, you're going to need something called a label. If you've never heard a label before, let me explain it as I go into it, okay? You're going to need a label for that. Inputs are relatively straightforward because you've already got them in the table, okay? Input there. Subtract the value stored in location num1. So you've got to go and fetch it first. So you've got to fetch num1 and get it from the current temperature. So you're going to need something to store the current temperature. So that, remember, num1 is the acceptable temperature, and that there is the input. So you're going to input the current temperature. If the remainder, so remember, remainder there sounds like it's some kind of like what's left over from a division, is greater than 0, then output value 1 to switch on the air conditioning. So you're going to output. We've got output again, haven't we? Which is just OUT. Okay. So you've got an if, then it says a loop there. So that really should be unindented. I'm like, why have they done that? Why have they done 2 loops? God, they're so ridiculous, these people. Yes, it does take more brain power, and I'm trying to help you. You've got to think computational. That's what it's testing here, people. That's what it's testing. So it says there, the assembly language used by the microprocessor has an instruction set which includes the following commands. So input commands. Input commands allow you to get information off the user. STA, that's store at position. Which position? So that says store at position Y. Okay, you can put anything you want in there. So for example, I could say STA temp. So think of it like store in a variable. So that for you, if you're writing something like Python, you'd write temp equals 14, right? That is the same as doing that store whatever value in temp. LDA is load at position. So what you're going to load? It says load the contents of location W into the accumulator. Does anybody know what the accumulator's for? ACC, the accumulator. Where is it based? It's based in the ALU, isn't it? Okay, it's for adding, subtracting, dividing, multiplying, that kind of stuff. Okay, that's where the accumulator's based inside the ALU. Yeah, you can do questions in any order you want. Yeah, stores the result of calculations. Thank you very much. Okay, so load the contents of W into the accumulator. Also, the ALU needs to get whatever data from the accumulator before it makes any calculations whatsoever. So it takes its data from the accumulator. So it has to load into there first before it can actually calculate anything. Okay, you've got sub Z, which means subtract the thing from register 0. You've got output X, which outputs whatever's in register X. BRP. Now these are your actual loops. Okay. Branch if positive. Does memory address in these questions only store one variable? Yes, it does. Yeah, you can have as many memory addresses as you like, but they always store one thing. Okay. BRP, label. So jump to label. You specify whichever label you want. So I could say label 1, num, loop, whatever. My loop could actually be called, have a label called loop on it. Right? I'll show you how I'll do that in a minute actually. Jump to label if the contents of the accumulator are 0 or greater than 0. Then it says jump unconditionally to label. So regardless of the condition, you're going to jump anyway. Now usually, I'm trying to figure out why I'd need that, but usually they put stuff in here that's extra that you don't need because it's expecting you to filter through them and figure out what you actually need. So I'm going to write my assembly language over here. Get rid of all this rubbish. Okay. Off we go then. Get my pen and let's start writing. So the first thing I'm going to do is I'm going to say input IMP. Let's store it in a variable. Let's use the same one we did in there. Let's call it temp. Okay? We're taking in, inputting the current temperature. Okay? Everyone happy with that so far? I know the questions don't have to be pseudocode written, but do you think it could write user code or something similar to write the code and then in assembly? Oh no, you could do if you've got time to write in pseudocode, then convert it into assembly. But it doesn't always pan out that way. You might get some marks for this. If you can't get all of them, then fine. But you know, input should be fair. It should be straightforward enough. Then what I'll do is once you've got the input of the temperature, you're gonna have to store it. So I need a STA command, and I'm going to store it somewhere. Now, what does seem strange to you is inputting temp is not actually writing it to a variable. So these two lines here, if I was to convert them into code, it would be temp equals input it'd be something like that. Those two lines of code do that, what you see on your screen there. They create a variable called temp. They get input from the user and they store it in a variable. Okay? That's what those two lines do. Then what I want to do is once it's stored in the variable, then I'm going to put the contents of the current temperature and I'm going to load it into the accumulator. And when I do these assembly language questions, I can picture this in my head because I've done millions of them, right? But I want you to picture all the variables that you've got, right? So this is the ACC. This is temp. Okay. And now what I've done, if I enter 14 degrees in there, and then I've loaded 14 degrees into the accumulator, that's the current stage of where I'm up to so far. I've inputted it, I've stored it, and I've loaded it into the accumulator. And what I'm going to do now is I'm just going to tick off. I've not done that yet. I've inputted that though, I've done that. Subtract the value stored in location num1 from the current temperature. So let's do this line then. Let's subtract that value then. I'm going to say sub num1. Okay, look what sub does. Subtract the numeric value in location Z. So subtract the numeric value in num1 from the accumulator. What's in the accumulator? Temp. So I'm taking the accumulator, I'm taking 14 in the accumulator and then I'm minusing num1 from it. And then it leaves the result in the accumulator. So the result of that subtraction there is left in the accumulator, and now I need to check if the remainder, so what's left over, is greater than 0. Okay? That I did before, that was wrong thinking. If the remainder is greater than 0, then output the value. So now I'm looking at this BRP, greater than 0, jump to label if the contents of the accumulator are 0 or greater than 0. So next, I'm going to introduce a branch if positive. And it needs to go to a label. Okay? Now I don't know what that label is yet because I've not finished the rest of my code, which is a bit tricky. So let me think ahead. So it's going to branch, it's going to jump if it's positive. So positive. So where do we want to go if the value is positive? What does it say in the question? Typically, the air conditioning system is set to regulate the temperature at 21 degrees. If the temperature rises above the required temperature, the system will be switched on to lower temperature. A control program for the air conditioning system is to be written in assembly language. The acceptable temperature is stored in 1. The required algorithm is. Okay, so it says here, if the remainder is greater than 0, so if it is bigger than positive, then we're going to output value 1. So I'm going to jump and output value 1. Okay, interesting. So let's do that. Going to output value 1. So I might say, just thinking here, people, LDA1 output. What am I outputting? I'll output the contents. Okay, right, I've got it. I think I've got it. Label. Right, let me explain this to you. What this does now, it says, if statement, if the remainder is greater than 0. So if this is true, you're going to jump to label 1. So it jumps to label 1, which is in here. And then label 1 says, load 1, which takes the number 1 and puts it in the accumulator. And then out will output whatever's in the accumulator. And you've just loaded it with 1. So it outputs 1. That logic is sound. Good. If people need me to re-explain that, I will happily do that. You can stick it in the chat. I'll happily explain it, re-explain it. But I've got things there. So I've done that bit now. I've done the if statement and I've done the subtraction. The only thing I've not done is I've not looped. So how do I get a loop in here? 14 is just the number that I've used just for this question. No. It's only given me 21. Okay. And technically, if you're given a number in the exam question, what I would do, you see I've used num up there, num1. I've not actually declared what num1 is. Temp gets inputted, so you don't have to declare that because you input it and then store it. But num1 has only been talked about in the question. I should really declare that. And if you want to do that in assembly, normally you say dat21, and that, its label for that is num1. So when you call num1, you sub num1, it goes and fetches your data. Dat stands for data. at position 21. So basically data 21, it takes that. So that's the label for that variable. That's how you store variables in assembly language. Okay. Using the BRA command, is that how you would loop? Okay, right, okay, good, yeah, that's correct. So if it doesn't branch if positive, so if it's positive, it'll jump down there. But if it doesn't, then I'm going to branch unconditionally. I don't need a condition. Branch unconditionally, and where do we want to go? Well, we want to go back to the start, don't we? We want them to enter another loop where the input is. So I will say BRA loop. So if it's positive, jump down there. If it's not positive, jump up there. Yeah, the only other thing you would normally do is normally you would end your code, and I think to end my code is this is underneath this output here, because if you've outputted it, then you've finished it, haven't you? You've done, because it says there just output the value 1, and then you're done. You'd finish that, wouldn't you? And then you'd go back down and finish. So if it doesn't meet the requirements, it loops to the beginning. Exactly that. So BRA means that it's not met the requirements, so go back and start again. BRP means it has met the requirements and it outputs 1, which turns on the air conditioning. Yep, you can improve your understanding in pseudocode first. Luckily they've provided the pseudocode for it, or they've provided the structured English for it, let's say, because that's all I basically lent on that there to guide me through the logic. I think I should clear it up a little bit. All this business. I think for success on this kind of question, what you're going to need to do is, one, you're going to need an understanding of logic. So what happens after what? And all the way through that, I was running that through my head. I was thinking, right, well, think logically. If you're sat in your holiday apartment and there's air conditioning, its job is to regulate the temperature and keep it at 21 degrees. So if it gets too warm, if it gets warmer than 21 degrees, then the air conditioning kicks on and it starts to cool you down, right? That's it. I'm thinking, I'm sat sipping Prime in my Barbados apartment, or whatever you crazy kids do nowadays, right? A control program for the air conditioning is using assembly language, and then it gives you the pseudocode for it. So what exactly is label 1? Is it the condition that the loop is set to meet? Okay, so label 1 basically says, if you meet the condition, if branch positive, if you've done the calculation for the sub 1 there, sub num 1, and it works out that it's a positive number, so if it's bigger than 21 degrees, then your apartment's too warm. What you want to do is you want to jump to label 21, which loads the number 1 into the accumulator and outputs it. That turns on the air conditioning unit and starts to cool you down. Prime is a luxurious beverage. Oh dear, 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 dear. Yeah, I think that deserves some sound.
And like a lot of us are really smart. I'm really smart.
I'm pretty sure that example is just one of many ways you can assign. It is. That's the standard way I write assembly language when I used to assembly program. I just have loads of dats everywhere at the bottom. Yes. Okay. Don't know if that helps or not. Again, I will put the mark scheme. I hope I'm correct here for the mark scheme. If I was marking this as an examiner, how would I assign the marks? So the first one is, if you can't get all these marks, what about some of them? 1, input the current temperature. So if I can I change my pen to green? Oh, I'm a computer scientist. Of course I can. Here we go. Right, so the first mark would come for inputting. The second one would probably come for loading the current temperature into the accumulator, because you're going to have to work on it. You're going to have to do some mathematics to it. Therefore, it has to be in the accumulator. Label 1, the BRP command, this one, if it fails the logic, it's going to jump. So that is this one here. That's your third mark. Then you've got your subtraction will be another mark, because you're actually making use of the accumulator and the arithmetic logic unit. You get 1 for outputting, so these two here would get you a mark because you've actually outputted it to everybody. And then the repetition loop, so this branch, if positive here, would also be a mark. 1, 2, 3, 4, 5, 6. Yeah, that's what. Yep, that's where I would assign the marks. No problem, Bob. So what if num1 is calculated and it is positive? It loads label 1 and then outputs it. So if num1 is calculated, yeah. So it depends what's returned from the num1 calculation, because that calculation is trying to detect whether the temperature is warmer than 21 degrees. If it's positive, like you say there, it loads label 1 and outputs it. That's exactly what happens. Label 1 is 1. So it puts the number 1 into the accumulator and outputs number 1 to the screen. And it switches on the air conditioner. Exactly. Yeah, you got it. Well done. Okay. Right, well, people, I think it's time to call it quits. I want to go home, like this on here. I want to go, there we go, there you go. Oh. Trying to get back to the main screen. Bear with me. I'm pretty sure I can just jump to whichever one. Why can't I just go back home? There's 390 odd slides in here, people, I think. There we go. We're back. Okay. Where does that sit us now? It's dying. My goodness. Great work, Diane. Good to see you. All right. Where do we find ourselves? We are days away. We are days away from our exam. What you do now, again, is very important, people. Structure yourself. Make sure you get plenty of sleep. You won't believe how important sleep is, especially to revision and motivation and concentration. Look after yourselves. Try your absolute hardest. I know you've got this in the bag. Hopefully, what I've done here in the past couple of hours has helped you a little bit. It's the reason why I do these live streams, to help the students out, to potentially get you where you need to go. I'll be on hand on Monday, somewhere in between lessons. If you've got any other problems or issues, just email me and I'll do my best to help you out. Please, a plea from me, make sure you got your ID card and you turn up for exams at least 15 minutes early. Settle yourselves down, because your mind, your brain, your body will be a bit panicky, a bit stressed. There's a lot riding on it, obviously. I'm sure you'll all do great. And thank you very much. Thanks for coming. I'll see you all soon. All right, stay safe.
And we say bye-bye.